Go ahead and get started. So welcome everyone to the last Cyberseminar presentation in the fall series on the Western United States drought on the ground and from space, combining in situ and remotely sensed data to understand and mitigate drought. So today we are very fortunate to have Narendra from NASA's Jet Propulsion Lab here with us. And Narendra is going to be presenting the current status of the SMAP mission and its application to agriculture. So Narendra was born in India and received a Bachelor of Engineering degree from the National Institute of Technology, Raipur in India, and a Master and PhD from Texas A&M University. So he joined the Jet Propulsion Laboratory in NASA and has been conducting research in hydrology and microwave remote sensing, especially for soil moisture. He is currently a member in the Water and Carbon Cycles group in the Climate, Oceans, and Solid Earth section at JPL. He is also a member of the Science Algorithm Development Team for the Soil Moisture Active and Passive SMAP mission. He is the Deputy Application Lead for the SMAP mission based in JPL. He works with the USAID for the NASA Server program to implement drought and crop forecast system for East Africa region. So Narendra, with that, we will go ahead and turn it over to you.
Okay, thank you, Emily, for the introduction, and that gave me the opportunity to start right away the presentation. So, to all the participants, if you have any question, you can just switch on your mic and speak to me. That's fine with me. You can interrupt me. So it's better to have a two-way traffic. And let me go.
Narendra, can you go ahead and expand? Can you go into PowerPoint?
Yeah, I will do that. Yeah, I'm going to basically do this. Okay, is that okay now?
Yes, perfect.
Okay, so I just wanted to put the slideshow now. So I'm mostly I'll talk about the status of the SMAP mission. Most of you or some of you may know about this mission, Soil Moisture Active Passive Mission. It's a NASA first decadal survey mission. And I'll mostly talk about what is the current status of the mission and how we can use the data in the agriculture application. And I would like to acknowledge my colleagues and my people who work in the project, like the Dr. Dara Intikabi. He is the science team lead, and I worked with him basically to develop the active passive soil moisture product for the SMAP mission. Then Dr. Eni Enzoku, he was my boss, and also he was the principal scientist of the SMAP mission. And Dr. Simon Yue, who is currently the science project scientist for the SMAP mission. With this, so the outline of this presentation will be, first I'll have some measurement approach reminders, mission status, and then SMAP surface soil moisture products. I'll show you what kind of products are there, what are its capabilities, and what we are doing to test it, some SMAP application, and SMAP data simulation potential, like with perspective to agriculture. Then I'll talk a little bit about the SMAP handbook, which is available online for free, and then the summary. So this is the outline of the presentation, and so this is the first slide, which tells us about the SMAP mission concept. On the left hand side, you can see there is a dedicated SMAP satellite proceeding in IEEE, which is the foremost paper on SMAP. If you want any reference, you can give this paper, basically written by Dr. Dara Intikabi. It's a big science team also there. So this was pre-launch actually. But now SMAP has been launched, there will be many papers coming up. But for now, if you want to use some reference, you can use this. And so what is SMAP? SMAP is actually soil moisture active and passive. So most of you probably know what is active and passive, or I will go and elaborate that further. Active and passive means, active means the radar part, that has an active sensor. It sends an emission and receive a scattered emission back through its antenna, a SMAP antenna, and the radiometer will just absorb all the natural microwave emission. So that's the active and the passive part, and SM stands for soil moisture. So that is how the name came into existence. And this mission was, uh, sorry about my typo, it is Will here because I was trying to, put slide together in a hurry. I'm in travel right now, but anyhow. So SMAP was supposed to provide a very high resolution soil moisture with global frequent revisit, uh, interval, but in a spatial and temporal sense. And as well as SMAP was supposed to provide high resolution freeze thaw state. But what happened? Unfortunately, we lost the radar, which is one of the important components, the active part of the mission. So that's why right now we only have 2.5 months of very high resolution data set, which we are working on. But we have a very high fidelity and working radiometer, and I will show you some of its results. It's working wonderfully, but the problem is we have a coarse resolution soil moisture product which is being collected regularly around the globe right from from the start of the measurement in April. So SMAP uses an L-band unfocused SAR and radiometer system that has an offset fed 6-meter lightweight deployable mesh antenna. You can see in this picture here, this part basically is the deployable 6-meter antenna. You can see it's a big rotating antenna. It rotates so there are many mesh antennas, but this is one uniqueness of this mission is that this antenna rotates at an RPM of 14.1. So that's the uniqueness, and that helps us to basically cover almost a swath width of 1,000 kilometers. So the radar has a frequency of 1.26 gigahertz, and it measures at VV, VHH, and HV, the cross pole, and its resolution is close to 1 to 3 kilometer right from the edge of the nether all the way up to the edge of the swath to edge of the nether. And the radiometer works at a slightly different L-band frequency, that is 1.4 gigahertz, which is a protected band, and it measures emissions, natural emission, microwave emissions at HV, horizontal, vertical, third stroke, and fourth stroke. And the radiometer resolution is close to 40 kilometer in 3 dB footprint. It has a conical scan. That means as it go forward in space and time, it has the scans the Earth's surface, going forward, and that is how it makes a 1,000-kilometer swath, as I mentioned before. And it has a revisit interval of 2 to 3 days. So every 3 days it will cover the whole Earth's surface, and it has right now has an exact 8-day exact repeat cycle. It has also a sun synchronous orbit. That means it passes the equator exactly close to 6 a.m. and 6 p.m. So suppose it is descending orbit, if it is coming from North Pole going towards the South Pole, then this polar orbit, which is called descending orbit, the satellite is passing over the equator at 6 a.m. And when it's going from ascending orbit, that means going from South Pole to North Pole, it passes the equator exactly at 6 p.m. local time. So any point of the time over a latitude, over not very high latitude, a latitude below 60 or 70 and below, the satellite is very close to 6 a.m., local time. So during descending and during ascending, 6 p.m. local time. So the choice of time is basically important because we want in our soil moisture retrieval algorithm, we want the thermal regime to be similar for the soil surface, for the plants, for the trees, and the water surface to some extent. So that's why we keep it 6 a.m. And if you look at some of the publications on the thermal profile of uh, uh, all the things on the Earth surface, which is very close, and they converge, at 6 a.m. So that was the logic of keeping it at 6 a.m., 6 p.m. orbit. And earlier the launch date was November 5th, 2014, but now it got launched in January 2015 after a couple of months of delay. So this is the objective and the objective of science objectives. and the requirements. So the science objective, decadal survey objective, that this mission should fulfill the weather forecast application, the climate prediction application, drought and agricultural monitoring, flood forecast improvement application, human health, and boreal carbon. So, and these application comes from, mostly for weather prediction, seasonal climate forecast, regional drought monitoring, crop outlook, river forecast modeling initialization, flash flood guidance, vector disease, seasonal outlook, and freeze thaw date for, carbon uptake or fixation. And the science requirements come from hydrometeorology, hydroclimatology, so if you put together all these things, we converged the whole everything converged to a baseline mission, which where the requirement was that soil moisture, if we can retrieve at 10 kilometer within 3 day spatial temporal resolution, and with an accuracy of 0.04 centimeter cube, that would be the best, and it may cover all the application mentioned in the above table. So that became, the baseline requirement for the mission. And also the freeze thaw, like at 3 kilometer detection at 3 kilometer with 2 day, interval, and 80% classification accuracy. And with these specifications, SMAP was supposed to meet, requirement of most of the, science requirements from hydrometeorology, hydroclimatology, and carbon. You can see the resolution requirement for hydrometeorology is 4 to 15 kilometer optimally, for hydroclimatology 50 to 100 kilometer, and carbon cycle 1 to 10 kilometer. So if we could have retrieved soil moisture at 10 kilometer, it would have met the requirement of all these applications. Now, these are the regions where what we did for active passive mission. So instead of 10 kilometer, we were retrieving at 9 kilometer. And this map shows you where the SMAP soil moisture algorithm was executed. This is the black portion is the portion where the algorithm works without any issues, but there are flags also. I'll talk about those later on. But the rest of the location, which we have white spot on, you can see not the white spot on the ocean or on the water body, mostly on the land. That is mostly due to the very high urban area like Los Angeles or New York. There is mostly such a built-up area. It's no way we can detect soil moisture, and we don't even understand the physics perfectly of the microwave emission from an urban city. So it was not at all possible. And other thing like mountainous region, very, very mountainous region, where it's very difficult to, get estimate of, incidence angle, as well as most of time the high mountains are frozen ground or have snow cover, and also the inland water bodies, as well as, so these are the typical, regions which you see white, but we do try to retrieve soil moisture over forest, like a region like Amazon, Congo, and these rainforest over in Borneo or in Indonesia, but the thing is that we can do we can't do a very decent job there, because microwave is kind of not transparent to very thick forest. What we detect is mostly vegetation status in those regions, but there are some possibilities that if there is an open area within that forest, there is a possibility of detecting soil moisture, but the limit is basically 5 kg per meter square water content. So the next plot will show you, that's the region where the SMAP is supposed to meet the science requirement of accuracy, resolution, as well as its spatial and temporal coverage. So you can see these are the black portion. These are the region where the vegetation water content is less than 5 kg per meter square. Urban area is less than 0.25 fraction. Water fraction is less than 0.1, I mean 10% within that grid cell, and elevation is less. Elevation slope standard deviation is less than 3 degrees. So you can see these were the regions SMAP were expected to meet the requirement, but the white region are the reason we were thinking we retrieve soil moisture, but we provide a flag there saying that the quality will be compromised because the algorithm may not function optimally in those regions. So these are some of the Oh, like I talked about the SMAP antenna. You can see this is how big the antenna is. It's a mesh antenna, and it was like our 7-minute terror, like in Curiosity mission when they landed on Mars. But this was our 7-minute terror. Opening of this reflector boom. Basically, the reflector boom opened, and then this reflector opened. So reflector is like collapsed like an umbrella, and it gradually opens up, and all the trusses you can see has to work in unison and perfectly, then only this condition is possible. And it opened successfully, and it's working amazing right now. So this reflector boom you can see, and you can see by the size of this by the people sitting and standing beside it. And then the right hand side the image is basically the satellite, which is a size of a minivan, you can see. And that's me standing in front of it. We paid a visit, but you can't recognize because I'm wearing all those masks and everything. But that is where the radar and radiometer is housed inside this box. It has star trackers and reflector boom, the cone which collect the reflections or from reflections from the reflector, and then there is a solar panel the other side, the black side, which you can see. Now SMAP was launched. I don't know whether you would be able to see this animation or not, but I made this for my daughter, and it goes something like this. I don't know whether you're able to see that or not, but it was launched on January 2015. And we had 3 months of in-orbit check, and during those 3 months, lot of instrumentations were checked, the electronics were checked, the solar panels were deployed, the antenna was deployed, and it started collecting data from the 1st of April. So I don't know whether you would be able to see this animation or not, but I will try to go ahead and play this. I don't know whether how good that would be, but I think that is not available so through this Adobe. So let's move out. So these are the products available through the SMAP mission. So you can see there are many types of product which are level 1 product, then level 2 product, level 3 product, and level 4 product. So level 1 product are directly the products coming from the instrument, from the satellite. So for our science perspective, for our application perspective, this is not a very important product, but for engineering perspective, for those who work in instrumentation and hardware, for them it is a very important data set, But and those who work in calibration of the satellite and all that, for them it is that's their holy grail basically. But there is some level 1 product which are like graded product basically. So level 1A and 1B are directly that this is the 1A is the raw data from the satellite, 1B is there is some kind of transformation from, but this is time ordered, still not gridded. Level 1C are the gridded instrument product data directly. And then level 2 is the product when we do retrieval on this level 1C data. That is the level 2 data. And level 3 is nothing. Level 3 is just composite of level 2 for one day. So for one day, there are kind of 14.5 orbits and half orbits. So we do a composite all the 14.5 descending orbit to make it level 3 data. And level 4 are the data assimilation of the satellite data with the model data, and those are the data called level 4 product, which is soil moisture root zone, surface and root zone, and carbon net ecosystem exchange product. So you can see the description of this product here on the middle, and then there is the grid resolutions are mostly radiometer at 36 kilometer, and you can see the radar is close to 3 kilometer. And then let me come to the classification of this product. One is the radiometer only product, which you can say L2 SMP, that means level 2 soil moisture passive only product. Then this is level 2 soil moisture active passive product. Then there is level 3 level 2 soil moisture active only product. But this product was not mandatory for in the mission, but passive and active passive were the required product for the mission. I made this green and red because green is the product which is currently available right now for the soil moisture. You know, so that is the product, that the radiometer only product, and radiometer is functioning nicely and which has amazing accuracy. So that product is currently available, gridded at 36 kilometer, and it is being collected from 1st of April. A level 2 products, we have nearly 2.5 months of data set, right from 15th April all the way to 7th of July. That is the day when the radar stopped working. But we have a wonderful 85 days of radar radiometer product, which is like we don't say it's a mission now. We just for make fun. We say global campaign, of radar radiometer only product. So which has a lot of science value. We can do a lot of science, but not a lot of application, because application require a lot longer time series of data set. We can't do anything, but we can do a lot of science studies, the interaction between radar and radiometer, and what all we can do in future to have similar kind of mission. And then there is a freeze-thaw product, which is level 3 product. This is also discontinued because radar stopped working. But right now we are working on a radiometer only freeze-thaw product that would be gridded at 36 kilometer. So this is this is all about the science product available through SMAP mission. But uh, the beta release of L2 SMP product is already done, and the data is available through NSIDC. I will talk a little more about it later on. So let me give you a little gist on the active passive approach, which was the core of this mission. And you can see we developed this active passive approach pre-launch using the airborne dataset, which has a radiometer and radar at L band. So the concept behind it is that the radiometer has a high accuracy, less influenced by roughness and vegetation, but coarser spatial resolution. That's its disadvantage. But radar, which has high spatial resolution, but are more sensitive to surface roughness and vegetation. So what we do, we blend these two, radiometer and radar information, to provide an intermediate 9 kilometer resolution with 0.04 centimeter cube by centimeter cube accuracy. So we take advantage of high accuracy of radiometer and high spatial resolution of radar, blend them in, and we come up with an optimal 9 kilometer product. We applied this algorithm, active passive algorithm. I published a couple of papers on that in IEEE TGARS. You can take a look if you are interested how we did that. And we applied in SMAP 2 region in Iowa, where it's mostly corn, soybean, and using a PALS, airborne sensor. And we found a very nice results, of 0.033 centimeter by centimeter cube RMSE when we implemented this algorithm over those fields. So let me show you this simple, same thing, of the field campaign. You can see what we do basically, we disaggregate the brightness temperature, coarse brightness temperature, using the high resolution radar. I don't go much in detail in that. If somebody have questions, they can ask me later on. So that's the whole concept. It was, you can see the radiometer coarse resolution. This is how it's applied in SMAP, which the level 1 CTB gridded at 36 kilometer. It is merged with, fused with, a radar, 3 kilometer, and ultimately we get a disaggregated brightness temperature at 9 kilometer, and then we retrieve soil moisture using ancillary data, and this disaggregated brightness temperature we get L2SMAP, retrieve soil moisture at 9 kilometer. But in this whole process, it also give us capability to retrieve soil moisture at 3 kilometer also. We can disaggregate directly to 3 kilometer using this fine resolution radar, but it has slightly higher noise and slightly higher error. So that's the algorithm which we used basically for active passive approach, and which we called disaggregation of active passive brightness temperature using active. So that's if somebody want more detail, I can talk later on. And it's the same thing. I'll skip. So this is a typical composite of soil moisture retrieved from SMAP mission, and this is the true soil moisture sometime in the time frame of sometime in July, I think, not in July, May or June. So you can see the distribution of soil moisture. It is very dry wherever it is expected to be, and it is very wet wherever it is expected to be. Like it is very wet, kind of wet over dense forest, and very dry over deserts, over arid regions. So the soil moisture distribution from the retrievals look reasonable. And you can see a very distinct feature, like it captured the rainfall event across Australia. There was a band of rainfall. You can see in that particular day it easily detected so that's the advantage of having a satellite based soil moisture. You can see these kind of thing. Also, another thing I will show you about the Texas flood here. I'll show you a couple of more images. It is so well captured, the Texas flood, through SMAP mission. At that time, the radar and radiometer were working. We were able to detect soil moisture at very high resolution at 3 kilometer, and detected very successfully detected the Texas flood. So this is a animation basically. It shows how we do resolution enhancement using active passive approach. So you see the detail captured by the SMAP active passive approach. So the first slide, the first image you see here on the top is basically the radiometer only, 36 kilometer grid soil moisture. Now this is the transition which become the 9 kilometer on top of that. And like you can see, when we apply active passive, it will give you more detail, information underneath information, that means a much higher resolution at 9 kilometer. In fact, we can go even detail with using the radar information, and this is at 3 kilometer. Now here you can see amazing details, where the soil is wet and why, maybe due to precipitation distribution you can see, or maybe due to other factor which influence soil moisture at a much finer scale. So the amount of detail you can see, I want to go through it again. It's over Africa region in Ethiopia. We saw a major precipitation event. We tried to capture it. You see this is 9 kilometer, from 36 to 9 kilometer, and going to 3 kilometer. So we have active passive 3 kilometer product, which shows that amazing detail this SMAP mission captured. Now you see the Texas floods I was talking about. You see the soil moisture in 3 kilometer. You can see the detail, amazing amount of detail we captured in Texas during that period, basically where we had a lot of flooding here in this region due to very high amount of rainfall. You can see some of the images below from 2015 during that period. So unfortunately, we don't have that capability now, but I just wanted to show you what SMAP was capable of. And now this is, see some of the 3 kilometer detail coming from this part of the world. Then see, this is some part of the Africa. From this part of the Africa, you see the detail, but there are some artifacts you can see directly here. You see this one? There is this one are the artifacts. So these are the satellite artifacts. This is not the, because underneath the nether, exactly under the radar, sorry, exactly under the satellite, which is called the nether region, that is where the radar doesn't work perfectly because of range and azimuth. And there, what happened is, like the way it sees the Earth's surface, it cannot, the SAR processing cannot actually detect the high resolution there at that just underneath the spacecraft. So that's why you see these kind of artifact, and which is actually flagged in the product, that don't use this soil moisture directly under the spacecraft. There is a caution flag already given in the product. Now this is the some part of India, and then this is Europe. You can see all this 3 kilometer product. And then coming to, I was talking about, beside the soil moisture information, we do give lot of quality information. So the quality information comes in two things. One is in surface flag, The other is, retrieval quality flag. So surface flag, as you can see, this is a swath passing over. You can see Africa, eastern and southern part of Africa, and you can see the surface flag on the right. It shows the surface static water body flag. So wherever there is a big inland water body like Lake Victoria, and all that, you can see the white color. It shows 1. So that means that particular the surface flag is actually is a 2 byte integer. Sorry, it's a 2 byte integer, and every bit has a information. You have to convert that 2 byte integer into bit, and every bit is related to one particular flag. Like the static water body flag is bit 0, and then we have the coastal flag, and anything close to the coastal area we flag it, because the radiometer footprint is big and it see a very wide region. So that's why sometimes has influence of water, which reduces the brightness temperature and confuses the algorithm. So that's why we have this coastal body flag close to the large water bodies. You see that this is the ocean, the Atlantic Ocean, and you see this is the coastal flag here, as well as across the large water body. Then we have urban flag, wherever we have large urban area, we have flags like you can see here. Oh, this may be somewhere, this may be some city in South Africa, maybe Johannesburg. You can see the urban flag popped up, and then you see the mountainous terrain flag wherever there are high mountains, where we think that soil moisture, we don't do a justice to soil moisture quality. We put the flag there for mountainous terrain, dense vegetation. So wherever we have dense vegetation, we put there. You see the edges of Congo basin, Congo forest, rainforest was here, so some of this got flagged. And then there's the nadir region. I was talking about a nadir region, just the area underneath the spacecraft. That is the nadir region. You can see a streak of white in the middle of this swath. So that is what the nadir region. So these are the basic. And then if you put together all this flag, and then some of the retrieval, um, limitations, maybe due to the parameter, maybe to the surface temperature. So this is the retrieval quality flag recommended. So the black regions are the regions where we expect the soil moisture meet the quality as well as the standard as well as the requirement. So you can see the retrieval quality flag is popped in all this, populated in all these regions. So we also have I talked a lot about the SMAP product, and the product was basically active passive, and passive product has similar surface flag and similar retrieval recommendation flag scheme. So there's the commonality there. And now in our SMAP program, we also have a big application development approach, where we have formed an application working group, developed application plan, hired a SMAP application manager, held application workshop at various home sites. So people are really interested in soil moisture product, especially high resolution, but unfortunately it is not there, but still they can use the radiometer only 36 kilometer soil moisture product to a great extent, and the efforts are on in JPL to enhance this resolution by statistical technique or by using some other satellite, so I'm involved in some of them. And then we have an early adopter program where they are adopting the SMAP data, right from the pre-launch period. We had some simulated data, we gave it to them, they developed the framework, and we have an early adopter program which is running successfully. Right now we have in the tune of 150 members, early adopters. So very successful application program going on right now, but we expect to see a lot more application users will start using SMAP data once the time series is developed. Like right now for radiometer, we have close to like 8 to 9 months of data set already there, which is freely available to anybody from NSIDC. So this is about the SMAP handbook. If somebody want to learn more about the SMAP spacecraft, its instruments, electronics, and then it's a soil moisture products, and its application, and all the papers published for this mission. It's all available in the SMAP handbook. You can go to the JPL website, Jet Propulsion Laboratory, SMAP, and then smap.jpl.nasa.gov, and there you can find this SMAP handbook for free, freely downloadable. And then there's the SMAP data portal at National Snow and Ice Data Center. As you can see here, this is where all the SMAP data will be available for free for anybody to download. And right now we have the passive only data beta released. It is available for free. Active passive data will be available from 15th November onwards, and those data will be for 85-day period, where until the radar functioned. And then and we will also have the assessment report, the user guide, and everything on that site. So once you get access to those things, you know how to use the data and everything. And in case in future you have any issues, you can contact me directly for active passive data as well as for passive data. So a case study I just wanted to show you. We did try applying SMAP like data set. So this shows what SMAP can do. So SMAP can work in conjunction with like various other satellite, like GPM, like MODIS, and so this shows basically different aspect of any hydrological or any geophysical models required. Like they require forcings, basically from like GPM is a rainfall, which is one of the most important forcings, and the SMAP and MODIS detect the a status of a particular state variable at that particular point of time, like soil moisture and vegetation. And these satellites, NASA assets, could be directly used in those kind of applications, like in crop modeling, and a simulation framework is one such thing where we can do that. And it can ingest all this information, and then we can also get climate smart information from climate seasonal forecast, and we used all this information in one of our projects, survey project, and we found very significant improvement if we use map like data set, especially not much improvement correlation, but great improvement especially in the RMSE of the crop yield, of the corn yield. If we don't use any SMAP like data set, what happens, you see if the RMSE is close to 4.7 tons per hectare, but using the soil moisture data set does help improve soil moisture, as well as the LAI data set from MODIS does help improve the yield, as well as because of better water and energy budget because of leaves and water status of the plant. So we found that results, and it was amazing to see these kind of results and what satellite can bring in, what kind of impact it can bring into these kind of agricultural model. And that's another study. This is the framework which is developed in Jet Propulsion Laboratory, which we developed a RAES regional hydrological forecast modeling system, which has crop models in there. And then what we do data assimilation of SMAP and the MODIS vegetation attribute into the crop model, and we get all the hydrological output from the hydrology model. Like with the model in the RAES framework is WIC. We get from there, we get meteorological forcing from GPM as well as from the hydrologic model, ingest them and do the data assimilation. And we tried to see how SMAP will behave. So what we did here, you can see we found a very promising results. This study was conducted when SMAP wasn't there, so we used SMOS and AMSR-E dataset, and we found very promising results. We show significant improvement in crop yield, and we published that paper in Remote Sensing of Environment. I'm in the second author, and my colleague Emo Reynes, he is the first author, and it was highly appreciated and one of the most downloadable paper at that time. So we see significant improvement using SMAP like data set. So the summary of my presentation now. So the SMAP mission, radiometer functioning normal, and radar is currently non-functional. The high resolution soil moisture at 3 km, 9 km available for 2.5 months. The coarse resolution soil moisture data is being processed continuously and are of high fidelity. Initial CalVal show close to 4% RMSE, which is close to meeting its requirement. L2SMP, which is a radiometer only product, a beta released and is available through NSIDC. L2SMAP, radar radiometer product, beta release will be done in November 2015, and focus and planned effort to promote meaningful applications. So it's going on in the SMAP mission. And we are also planning to provide an enhanced resolution product using the radiometer only product or by using other satellite radar data. So with that, I come to an end of this presentation. If you have any question, you can ask me.
Great, Narendra. Thank you so much. That was an interesting presentation. We're going to go ahead and move to the Q&A part of the seminar, so everyone can have their questions in the chat box, and then I'll just read them off as they come in. Okay, so I see a question coming in from Chuck Slaughter. He asks, based on your early slide depicting white areas of non-coverage, it appears that a major share of the circumpolar northern boreal forest, say 55 north, 68 north, is not actually covered, despite the mission statement about the boreal carbon flux. Narendra?
Okay, so I actually was talking in this context mostly about soil moisture, not on freeze thaw. So what happened, this boreal forest has vegetation water content more than 5 kg per meter square. But but we do retrieve soil moisture over there, and when the freeze thaw happened during the frozen period, the SMAP will detect the frozen state, as well as that will be used for our carbon product, carbon fluxes. So the freeze thaw product is basically used there. This map is mostly for the soil moisture, where SMAP is about expected to meet the soil moisture requirement. So I hope that answered my question, your question.
We see someone else typing. A few more questions will probably come in. Sorry if I say your name incorrectly, but Ardashir asked the question. First, thanks for the great talk and informative presentation. Is there any plan to release the available radar level 2 retrievals for those operating months before January 2016? How can we access them?
Okay, so we have this radar and radiometer, active passive, which is radar radiometer product, as well as active only product, which will be released through NSIDC. Those are only for 85 days from 15th of April all the way up to 7th of July, and it will be released this coming month, November 15th. A beta release will be there, so it will be accessed to public for free from NSIDC website.
Another question came in. Without the radar, I wonder what would be the resolution of level 4 products. Still 9 kilometers?
So it's a great question. What happens is the modeling frame will work at 9 kilometers. So it has the forcings and other ancillary data like soil and all that at 9 to 10 kilometer. So the model actually work at 9 kilometer. Even the GPM forcing now they will be using is close to 10 kilometer. So the model output is at 9 kilometer, but the assimilation is done in 36 kilometer and propagated to 9 kilometer. So still the level 4 product will be at 9 kilometer soil moisture as well as root zone.
Okay. Another question coming in. Okay, a simple question, and perhaps you covered this already, but is GRACE the same as SMAP, and or how are the two related?
Okay, a simple question perhaps because but is grace the same as that? Oh, actually, they're totally different. GRACE and SMAP. GRACE is a satellite which measures the gravity of the Earth as a whole, basically, right from the center of the Earth to the top of the atmosphere. What would be the gravity of the Earth at that particular point of the time on the surface? So, gravity experienced by Earth at that particular point on just underneath the satellite. So, it measures gravity, and like whenever there is like, and mostly from the hydrology perspective, we use GRACE basically for detecting change in groundwater, as well as the change in like ice masses over Greenland. So it detects the gravity, and if there is change in groundwater, you see the change in gravity, and that means reduction in, suppose the gravity reduced, that means the groundwater level has reduced, in that region. As well as if the ice sheets are melting, it detects that, the gravity of that region is reducing. That's the telltale sign of the, that ice sheet are melting in Greenland. So it gives, and the resolution of GRACE is very, very coarse, in the tune of 250 to 300 kilometer, and you get a relative estimate. Okay, it don't give you an absolute value; it give you a relative estimate. Okay, the groundwater might have reduced by this much, in that particular coarse resolution. So GRACE give us an estimate in a hydrological perspective, the amount of groundwater increased or reduced in a particular region. But SMAP is totally different. SMAP measured the microwave emissions coming from Earth naturally, as well as through radar. So radar is not working now, but that is how it worked. And it gives you the soil moisture of top 5 centimeter only, the SMAP mission, because the microwave emission coming from the surface is mostly from the top 5 centimeter. And it doesn't work in a very highly vegetated region, but it does work in mostly moderately vegetated arid regions, and moderately vegetated and arid regions. So there is a big difference between SMAP and GRACE. GRACE is mostly about for groundwater at a very, very coarser resolution at 250 kilometers. It can give you a regional perspective. Okay, what is happening in a region? Like in a river basin, it can give you, okay, what would be the increase or decrease of groundwater. And SMAP give a very high resolution soil moisture estimate globally. So I hope that answered.
Great. So we're going to wait a few more seconds, see if more questions come in. It looks like we're wrapping up now. I don't see any typing going on. Just want to thank everyone for participating today in the seminar. Just to remind you, this is being recorded, so we'll have it posted online within the next week. Thanks again, Narendra, and I think we can close out from here.
Thank you very much.
Great. Thanks a lot.
Thanks. Bye.
Bye-bye.